Hello, this is the video for Advanced Chemistry 2, CHM 146, in preparation of your first exam of the semester. I'll be covering the review sheet contents, which I've distributed already to you, either in class or in email. So get that handy if you could, please. Dig it out, because that's what I'm going to go over, are the 16 problems that are on the review sheet. I'll give you a rough guide to how to solve each one of these problems, maybe do some of the calculations, but at a minimum give you some of the formulas that would be involved. And then as I wrap up the video, I'll describe what you should expect on the first exam and the structure of the exam. All right, let's get started then. Of course, exam 1 is going to cover the contents from chapters 5 and 6, which we've talked about in class already. Chapter 5 is the gas laws contents, and chapter 6 is thermochemistry. So these 16 questions that I've put on the review sheet are relevant to those various topics. So our first question is, how many joules are equivalent to 235 calories? So a real quick conversion, right? Now this is a calorie with a lowercase c. And we know that 1 calorie is 4.184 joules. So all we need to do is this quick, easy multiplication. This is sort of like a warm-up stretch for us. And we have 983 to the same number of significant figures, 983 joules. All right. Of course, there are a variety of other units that we associate with energy, and so be prepared to do any kind of unit conversion. The conversion factors would be provided on the exam for you. I haven't asked you to this point to memorize any of those conversion factors. Our second question: if 1 mole of ethanol at 22 degrees Celsius absorbs 1.45 kilojoules of heat, what's the final temperature of the ethanol? And we're provided the specific heat capacity. So heat, when it enters or leaves a system, can be quantified with two formulas. And when there is a change in temperature of the system, we need the M times CSP times delta T. Okay. Now we're asked for the final temperature, but that's going to come from first finding the delta T, the change in temperature. So this would be Q divided by the mass of our ethanol and the heat capacity. The heat that we're given is 1.45 kilojoules, which I will convert to 1,450 joules, right? Oops. Because the joules will need to cancel with the heat capacity units down here in the denominator, 2.44 joules per gram degrees Celsius. If I hadn't done this conversion, I'd be off by a factor of 1,000, and it would predict a very small quantity or temperature change. So my 1 mole of ethanol, I'll do this out on the side here. Ethanol is CH3CH2OH, and so a mole of ethanol would weigh, I'm going to rough this out, 12, 24, and 6, so 30 and 16, so it should be about 46. We probably have about 0.03 given the various components of the hydrogens and carbons. All right, 12, 24, 40, yeah, 46. So that means we've got 46.03 grams of ethanol, which come up here to be our mass. So we'll take our 1,450 joules divided by both the 46.03 and the 2.44, and we come up with a change in temperature of 12.9 degrees Celsius. Now, our change in temperature, right, is our final temperature minus our initial temperature. So our final temperature, which is what we're asked, would simply be the delta T plus the initial temperature. So T final is this 12.9 plus our initial was 22.0. So 34.9 degrees Celsius should be our final temperature for this sample of ethanol. Okay. Let's move on to our third question. If 46.1 grams of zinc is placed into some water, what is the final temperature of the mixture? So this is a calorimetry experiment. We've placed a, looks like a cold piece of metal into a warm or hot sample of water, and we'd like to find the final temperature of the system. So this is sort of the most algebraically involved version of this type of problem. We've got heat lost by one material and then heat gained by another material. And the only thing that's different between those two quantities is the sign. One would be a positive and one would be a negative. So to make them equal each other, we need to multiply one of them by a negative. So our water is what's going to cool down. Now our zinc is 18 degrees Celsius to start. Our water is 75, so we know our final temperature is somewhere between those two. At any rate, both are experiencing change in temperatures. So again, our MC delta T will be the formula of use here. So for the water, it would be negative mass of the water times the heat capacity of the water times the change in temperature of the water. And for the zinc, it would be mass of the zinc times heat capacity of the zinc times the change in temperature of the zinc. Now, we're after the final temperature, so we have to break this out a little bit further to T final minus T initial of the water. And on the zinc side, we can add in place of the change in temperature, T final minus T initial zinc. Now notice that I've specified each substance as having a unique initial temperature, temperature initial of the water, temperature initial of the zinc, but I haven't put that specific label on the final temperature because the two substances will have the same final temperature. So I don't need to say temperature final water, temperature final zinc. They are the same thing. All right? And we're ready to substitute in our numbers here. On the water side, we are told 80 grams of water. The heat capacity of water is 4.184 joules per gram degrees Celsius. T final minus, it was 75 degrees Celsius for our water. On the zinc side, we've used 46.1 grams of zinc. The heat capacity of zinc is 0.388 joules per gram Kelvin or degrees Celsius. Again, T final minus, its initial temperature was 18 degrees Celsius. So at this point, it just becomes an algebra exercise. This is your unknown. We've got to do some multiplication and distribution here. So we're going to have negative 334.72 times the final temperature plus 25,104. And on the right side, we're going to have 17.89 times the final temperature minus 322. So let's just group our like terms together. Take 25,104 plus 322. On the right side, I've got 25,426. And on the left side, I'll take my 17.89 plus my 334.72. 352.61 final temperature. Divide by that coefficient. And we come up with 72.1 degrees Celsius. Again, does this make sense? We had a 75 and an 18, so 72 is between that. And this temperature is heavily skewed towards the water, as is often the case, owing to the fact that water has the much larger heat capacity. So it's a lot harder to change the temperature of the water. So often in a calorimetry setup, there's another little hint for you. The final temperature ends up often being closer to what the temperature of the water was initially. Okay. Question 4. 27 grams of an unknown metal is at 88.4, placed into some water. We're given the final temperature. What's the heat capacity? So another calorimetry problem here. Again, the heat is going to be M CSP times delta T. This time we're after the heat capacity, so Q is going to be M divided by the delta T. Let's see. Whoops, sorry, I got a little bit ahead of myself. Sorry. Not quite right. I need to start with this similar setup. Again, Q lost, the negative of that is equal to the Q gained by another substance. All right. In this case, it's the metal that is losing. So negative mass of our metal, CSP of our metal, times the change in temperature of the metal, equals the mass of the water, CSP of the water, times the change in temperature of the water. So we can solve for the heat capacity of the metal. It'll be the mass of the water times the heat capacity of water times delta T of water divided by the negative of the mass of our metal and its change in temperature. Now I'm ready to plug in my values here. For my water in my calorimeter, it was 115 grams. 4.184 again is the heat capacity. Change in temperature of the water. Initial temperature was 21, final temperature is 23.7, so we need to do final minus initial. Mass of our metal was 27 grams, and its final temperature was also 23.7, minus its initial temperature, 88.4. Again, that's going to give you a negative value for change in temperature. But we have this negative sign from the initial equation, and that's going to cancel out. So let's get to work on the calculation then. 23.7 minus 21 times 4.184 and 115 divided by 27 and 23.7, the change in temperature. And I come up with 0.74, and that would be joules per gram Kelvin or degrees Celsius, since we are working in degrees Celsius in this case. All right, so that's the heat capacity of the metal. Again, a way to identify an unknown substance, getting one of its properties that you could then consult a table of known properties of metals. Question 5. Now we're going to start to use some of the other form of our heat flow formula. 1 gram of decanol is burned in a bomb calorimeter whose capacity is 924 joules per Kelvin. The calorimeter has 1.12 kilograms of water whose final temperature is rises from 21.8 to 24.68. Find the enthalpy of combustion of the decanol. So there's a fair amount of work that's going to be involved in this question 5. Again, the idea is that in a calorimeter, in a bomb calorimeter, we could set this up a variety of ways. You've created your own little universe where the total change in energy is 0. And there are a couple of different pieces of your universe. In this case, we've got a reaction. You've got the bomb. And given that we're told specifically about the amount of water, we have the heat transferred to the water as well. So this would lead us to a very similar equation, except that now instead the reaction is equal to the negative of the heat of the reaction is equal to the sum of the heats of the bomb and the water. The bomb heat is just its calorimeter constant times the change in temperature, and the water's heat is once again mass times heat capacity times change in temperature. All right. Now, depending on how much we want to do here, we could group a lot together, but ultimately this Q for our reaction will be N times delta H of the reaction as well. So we could go ahead and solve, if we want, all symbolically. There's a variety of ways to do this, though. We could put all our numbers in at this point or leave everything as symbols. C calorimeter times delta T. We got our M, CSP, delta T of our water. All this will be divided by the negative of our moles. So our calorimeter constant was 924. It's going to be joules per Kelvin. Although because our temperature change is a delta, it's a change, it doesn't really matter that we're in Celsius or Kelvin. Our change is 24.68 as our final temperature minus 21.81 as our initial temperature. So we could say that's in degrees Celsius. I could just change this to per degree Celsius so our units cancel. For our water, it was 1.12 kilograms, so that needs to be in grams, 1,120 grams of water. Again, times our good old 4.184 joules per gram degree Celsius. And it's going to experience the same temperature change, 24.68 minus 21.81 degrees Celsius. All this is going to be placed over the 1 gram of decanol. So now I need moles, so I'll take my 1 gram of decanol times its molar mass. So 1 mole of decanol, the formula for decanol is C10H22O. So 10 times the molar mass of carbon plus 22 times the molar mass of hydrogen plus 1 oxygen is 158.276 grams. It's going to be a very small number of moles that we have there. So when we're all said and done, this delta H is going to be, I know it's going to be a negative value. It's an exothermic reaction, I can tell, because it made its surroundings temperature increase, right? The water and the bomb went up in temperature. That's because the reaction released energy. So 24.68 minus 21.81. It's a 2.87. Just want to jot that down to myself since I'm going to use it twice there. So 2.87 times 924 plus the 2.87 times 1120 and 4.184. So my numerator is about 16,100. All that is going to be divided by 1 divided by the 158.276. And I get huge number here, 2548390. That is joules per mole, or in a kilojoule scale, because we often express these in kilojoules, this would be negative 2,548 kilojoules per mole. Okay. And to 3 significant figures, that would be 2,550 or 2.55, which is what I've put in the answer key on your sheet. All right. Question 6 is also a bomb calorimeter. In question 6, the big difference, though, is that the calorimeter is not distinguished from the from the water like we had over here. So it's actually going to be a little bit simpler. In question 6, our delta E is just the Q of our reaction plus the Q of the calorimeter as one total system. So negative Q reaction equals Q of our calorimeter. Now let's look at our details here. We've got a 1.435 gram sample of naphthalene. We've got the temperature change. We've got the heat capacity of the bomb. Again, determine the heat of combustion. So this is going to be N times delta H of this reaction. And on this side, it's just going to be C of the calorimeter times the delta T. So the enthalpy of reaction is going to be C calorimeter times its delta T divided by the negative of moles of the naphthalene. So we've grouped everything together to get our calorimeter constant, 10.17 kilojoules per degree Celsius. Okay, we can leave that as kilojoules because we're not getting any kind of unit cancellation here, and then our answer will already be in kilojoules. Sort of like there, we had to convert it to joules. Our change in temperature, 25.95 minus the initial 20.28 degrees Celsius, divided by, again, the moles. I'm going to have to do this conversion. 1.435 grams of naphthalene I've got to figure out the molar mass of my naphthalene. It is C10H8, so 10 times carbon's molar mass plus 8 times hydrogen's molar mass. 128.164 grams are a mole of naphthalene. So this enthalpy of reaction, 25.95 minus 20.28 times the calorimeter constant, 10.17, divided by 1.435 converted to moles, so divided by 128.164, sorry. And I come up with negative 5,150 kilojoules per mole. If we were leaving this in joules, it would be times 10 to the 6th, but this is 5.15 times 10 to the 3rd kilojoules per mole, as I've put on the answer key. All right, 7. Beginning with 7 here, we have a reaction. We got a thermochemical equation for the combustion of hexane, and we'd like to know what is the heat flow for the combustion of 2.5 grams of hexane. So the heat flow in some reaction is equal to N times the delta H of that reaction. So we need to first find moles from our 2.50 grams of hexane, C6H14. So again, we'll do some adding up of our parts here. 6 times the molar mass of carbon plus 14 times the molar mass of hydrogen. Looks like 86.172 grams. And then we multiply by our delta H, which is negative 8,326 kilojoules. Now I have to check the chemical reaction. So if you're looking at the page, you see that the coefficient of hexane, which is what we're trying to cancel out, right? Moles of hexane right now, is 2. So this amount of energy, according to that chemical reaction, is in relation to 2 moles of hexane, not just a single mole of hexane. And so you need that coefficient of 2 there to get the proper energy ratio. So it's just a matter now, 2.5 divided by the molar mass times the 8326 and divided by 2. We get negative 121 to the 3 sig figs that we can have. Negative 121 kilojoules of energy would be the heat flow. The negative sign means that this energy is released by this reaction. Okay. All right. Number 8. So this was 7. Number 8 is an example of Hess's law. Determine the heat of reaction for the oxidation of iron given the equations that we have listed here. So we've got 3 equations that we need to combine here. Let me get them a little closer so I can see them. Our overall goal, as you could see from the paper, is to have a coefficient of 4 on iron. So if I look at the 3 puzzle pieces, as I like to refer to them, only one of them, the first reaction, has iron in it. So I'm going to need that reaction used in its forward direction in order to maintain the iron on the left side of this reaction. So that's 2 iron plus 6 water, which will produce 2 iron 3 oxides, it looks like, or hydroxides, yeah, OH3, all right, and some hydrogen gas. All right. Now I need this whole thing to be doubled though, because my overall reaction is calling for 4 irons. So what that means is that in the delta H column, I would have to double the energy of this reaction as well, which is positive 321.8 kilojoules. All right, let's see what's next. Oxygen. Well, I've got oxygen only in the second reaction. It's on the product side, so I'm going to have to reverse that reaction. All right. So my second reaction, I'm going to change its direction. So this would be 2H2 plus O2 to make 2H2O. And I also need 3 oxygen, so I believe I'm going to have to triple this entire reaction. So I've done 2 things to that reaction. I switched its direction, which would introduce a negative sign or change the sign of its energy, and I tripled it. So I'm going to multiply its energy by -3. Its enthalpy change was -571.7 kilojoules. All right. And then finally, I need my iron 3 oxide, Fe2O3, on the product side. It's on the reactant side of this third reaction. So I'm going to, again, flip that reaction. So this would be 2 FeOH3s would change into Fe2O3 and 3 H2O. My overall reaction needs 2 iron 3 oxides in it. This only produces 1. So again, I'm using a coefficient. I've got to double that. So I switched the direction, negative sign. I doubled it, multiplied by 2. The original energy was a positive 288.6. Okay, kilojoules. So let's see, did this all work? All right. Well, I know my iron's not going to cancel out. I've got 4 irons, which will come down to the bottom. All right. I have a total of 12 waters right now, if I did this correctly. Yes. I've got a total of 12 waters in this reaction. So there's 12 on the left side. But I have 6 on the right from this reaction and 6 on the right from that reaction. So all the water canceled out. Takes a little bit of time to make sure that some of these things cancel out. How much hydrogen do I have? I have 6 units of hydrogen on the left, and from the original reaction, top one, I have 6 units of hydrogen on the right. So the hydrogen goes away. And my oxygen is going to come down. 3 moles of oxygen will come down. It doesn't cancel with anything on the right. What else? I have 4 units of iron 3 hydroxide and 4 units of iron 3 hydroxide. So that will cancel out. And all that leaves then on the product side, remembering to distribute, is 2 Fe2O3s. So I have successfully matched the coefficients and the components of the target reaction. So now I can add together my energies in the same fashion that I added these together. So I just need to take 2 times the 321.8 plus a -3 times 571.7 plus a -2 times 288.6. Okay, and this gives me delta H for this reaction of -1648.7 kilojoules. -1648.7 kilojoules. Okay. All right, we're on to the back side of the sheet, halfway through our problems. Number 9. Calculate the enthalpy of reaction. This time we're going to use standard molar enthalpies of formation. So the sort of the shortcut for Hess's law, the pattern that's at play, if we use formation reactions, is to add together the enthalpies of formation of all of our products and subtract the enthalpies of formation of all of our reactants. All right. So for this reaction, our products are carbon dioxide, and we've got 2 moles of carbon dioxide. So I'm going to take 2 times CO2's value of -393.5. And we have 3 moles of water as a vapor, so -241.8. All right. And then I'm going to subtract from the reactant side. I need just 1 mole of ethanol, so -235.3. And then I do have 3 moles of oxygen, but since oxygen is an element, its enthalpy of formation is 0. So really we don't even need that component right there. Now we just add these up as we've written here. 2 times -393.5 plus 3 times -241.8. It's about -1500. all that we're going to... Okay, I saw that the video camera shut off. Again, we were finishing problem number 9 here, and I'm not exactly sure where it cut off, so if we didn't see it before the last segment ended, the enthalpy of this reaction was negative 1277.1, simply carried out the combination according to Hess's law of adding together the product energies and subtracting the reactant enthalpies of formation. Okay? All right, what do we have for number 10? We've got enthalpy of formation. What is the amount of heat released when so many grams react to produce ammonia? Okay, so we've got some stoichiometry involved here. So we need a balanced equation to do this reaction. So when we form a single mole of ammonia, a single mole of ammonia, NH3, so that we can use the enthalpy of formation value that we're given in this problem, which is negative 45.9 kilojoules per a single mole of ammonia. This is going to be a little bit different, but our reaction would be 1/2 of a mole of nitrogen, right, plus 3/2 of a mole of hydrogen gas to produce our ammonia. Okay. So this is a limiting reactant problem. We'd like to know what is the energy produced when we've got these two different quantities. Now, there's a typo I see in this problem. The nitrogen should be a gas. All right. So what we have to do anytime we're faced with a limiting reactant situation is determine which is our limiting reactant, and we're going to do that here by just calculating for each quantity the Q, and the smaller Q would be associated with the limiting reactant. Just like in chemistry 1, you could take each reactant quantity and figure out what product quantity would be made, and the smaller product quantity is the one that would actually be made, right? Because your limiting reactant would run out. So if I do this for the nitrogen, N2, all right, the mass of nitrogen that we're using is 5.38 grams. I need to convert that to moles. A mole of nitrogen is 28.02 grams. And then I would multiply by the negative 45.9 kilojoules. Now here's where that's sneaky, because that's per 1/2 mole of nitrogen, or 0.5 moles of nitrogen. Right? Just like in a problem that we had earlier when we had to reference the coefficient, unless we're going to change everything and scale these all up, in which case the energy would scale up, it's perfectly fine to take this quantity of energy as long as you associate it with this coefficient of nitrogen. All right? And so it does make your numbers a little bit sneaky, but you got to take 5.38 divided by 28.02 times 45.9, all negative, and then divide it by 0.5. So multiply by 2. And I get negative 17.6 kilojoules can be produced if all of the nitrogen is used. Now we repeat with the hydrogen quantity, so 3.32 grams of hydrogen. Of course, hydrogen has a much smaller molar mass. A mole of hydrogen is only 2.016 grams. The same negative 45.9 kilojoules would apply, but now it would be in association with 1.5 moles of hydrogen. So we'll take our 3.32 divided by 2.016 times the 45.9 divided by 1.5. And if all of the hydrogen is used, negative 50.4 kilojoules of energy could be released. So our nitrogen is our limiting reactant, and the quantity of energy that can be evolved is the 17.1 kilojoules, or 17.6 is what I seem to have in the, 17.6 kilojoules of energy can be released. All right. All right, that looks like it wraps up the chapter 6 questions. We had them on this sheet first. Now we're going to look at 11 through 16. These are going to be our chapter 5 gas law problems. So number 11. The lid is tightly sealed in a rigid flask, 3.5 liters of hydrogen, 17 degrees Celsius, 0.913 atmospheres. The flask is heated. What's the pressure? So this is some code language here. Key words. A rigid flask. Its volume is not going to change. So technically I could be using my combined gas law here. But the volumes are going to reduce or drop out because they're equal. So we're asked for what's the new pressure in this flask. So P2 will be P1 times T2 divided by T1. So our original pressure was 0.913 atmospheres times our second temperature. Now we have to put these temperatures into gas laws. So 71 plus 273 is 344 Kelvin. Sorry, we have to put the temperatures into gas laws. I meant to say we have to put the temperatures into Kelvin to use them in our gas laws, owing to the fact that negative temperatures exist on the Celsius scale, which means it's not an appropriate scale for gas law work. And then our original temperature, our 17 plus 273 is 290 Kelvin. Okay. So now we just need to crank this calculation out. 0.913 times the 344 divided by the 290, and we get 1.08 atmospheres. Does it make sense? Pressure and temperature are directly related. So as the temperature was raised for this cylinder or this flask, the pressure should have increased, and sure enough, it did. Okay. All right, number 12. We've got a flask with some methane in it. We're given the temperature and the pressure. What's the pressure if the volume is increased and the pressure is decreased? So another application of the combined gas law. This time, all the variables are in flux. All right, and so we won't cancel out anything. And we're asked for, again, P2. So we've got P1, V1, T2 divided by T1 and V2. Okay. So we just need to get everything into the right position here. So at number 12, our original pressure, all right, is 318 millimeters of mercury. And it's fine if we leave this in millimeters of mercury. The question has not specified use atmospheres or answer in atmospheres. Our volume was 0.225 liters. Our new temperature, our second temperature, 95 degrees Celsius. So that's 368 Kelvin. Our original temperature for this gas was 27 degrees Celsius, so 300 degrees Kelvin. And our new volume is 0.5 liters. Okay. Now if we want to rough out what our answer might be, the volume increased, so the pressure should decrease according to that. And the temperature increased, which should cause a pressure increase. So there is a sort of conflicting trends there, although the volume more than doubled here. The temperature did not double from 300 to 368. So the volume is the dominant change in this context. And so I would predict a pressure decrease due to that volume increase. But let's find out. 318 times 0.225 times 368 divided by 300 and divided by 0.5, we get 176 millimeters of mercury. So our pressure decreased, again, largely driven by that volume increase that we see. All right, 3/4 of the way there. 13. We've got a flask with a certain volume and a pressure defined. We know the same number of moles as in another flask. What is the temperature if the SO2? All right. So if a 3.44